Alright, so now let's look at algebraically overdetermined or underdetermined systems. So first of all, here's our first example. This just basically has to do with all the different types of solutions. So they may be overdetermined or underdetermined or, like Mama Bear soup, just right determined. So this is three equations, three variables. If we plug it into our calculator, we use this augmented matrix. Using the RREF function produces this, which you know corresponds to this. Now, why is that no solution? So let's look at that for a second. This is really 1x plus 0y plus 0z equals 0. So that's the equation x equals 0. This would be 0x plus 1y plus 1z equals 0. So that's y plus z equals 0. And yeah, that can happen. But this is 0x plus 0y plus 0z. 0 plus 0 is 0. 0 equals 1. Whenever you get 0 equals 1, that tells you you cannot have a solution. That's algebraically what happens when there's no solution to a system. Now let's look at what happens when you graph it. If you were to graph these three equations, it looks like this. Here's the first, here's the second, that's there, and here's the third. Alright, so all three of those hit, but you can see, look in the center part there, see how they don't all three meet in the center. So their lines of intersection are parallel, so they're never going to all touch in the same place. So that's a picture of no solution. In our next example, we have three equations with three unknowns. Plug in the augmented matrix and RREF it, and it gives you this solution matrix, which isn't just the ones across the diagonal, so it's not a unique solution, but it's actually infinite solutions. So why is that infinite solutions? Let's talk about that for a second. So this top line is really 1x plus 0y plus negative 1z equals 0. And then we have 0x plus 1y minus 1z equals negative 1. And then all 0, so we don't even care about that line. Right? So we actually don't really even care about the 0x or the 0y. So then that just gives us this equation here. X minus z equals 0 and y minus z equals negative 1. Okay, so here's where it gets a little tricky. So there's infinite solutions because this relationship is our solution. So since that relationship is our solution, there's an infinite number of points, x, y, z pairs, that would satisfy that relationship. So what we're going to do, every time we have one of these types of questions, or anytime I have a system of equations on your test, what you're going to have to do is always have an answer that looks like x equals y equals z equals. So for traditionally, you're going to get x equals, I don't know, some number, and some number. But in these cases, these special ones, you don't get that. But how do we get an x equals y equals z equals? Well, see that they both have z here? So if I were to add z to the first equation, that would give me, if I added z on both sides, that would give me x equals z. So whatever z is, the x has to be the same coordinate. And then if I add z to this one, that gives me y equals negative 1 plus z. So whatever the z coordinate is, that gives me the y coordinate has to be 1 plus that, or negative 1 plus that. So that's this set of equations here. So when I want x equals y equals z equals, well, z can be whatever it wants, and we don't just call it z, we call it some other variable. So don't get all confused by this. I'm just going to pick another variable, call it a. So if z is some number a, then y has to be a minus 1, and x is the same thing as z, so x is a. So on your test, I'll ask, what are some example solutions? Well, an example solution is if z equals, let's say, 1, well, then y is 1 minus 1 is 0, and x is the same thing as z, it's 1. If z is 56, then y has to be 1 less than that, so it's 55, and then x is the same thing as z, is 56. Those are just two examples of the infinite number of solutions. So now let's see what that looks like graphically. So here's the graph of the three equations. So those three equations are these three equations. And this is how it looks. So you can see the three equations all intersect. And if you look right on the end here, they all intersect just on a line right there. So actually this line is where all three equations meet. Therefore, infinite number of solutions. Just a couple more quick examples here. So here's two variables, so two-dimensional system, but three equations. Here's your augmented matrix, and here's what you get when you plug it into your calculator. So what's this going to be? Hopefully by now you figured out this is no solution, because 0x plus 0y, so 0 equals 1, can't happen. This is what that would look like. If we graphed all three of the lines, this is what they look like. There's no place that all three of the lines meet. So next example. So here's four-dimensional system. 4 dimensions because there's x, y, z, and w, so there's 4 variables. Here's the solution that your calculator would spit out. So now your calculator has spat that out. So this is x minus z minus w equals 0, da 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 da. So there's no 0 equals 1, so there is a solution, but it's dependent. And since there's 4 variables and 3 equations, there's absolutely no way that there could be one solution. So this augmented matrix, or reduced matrix, gives us this system of, right, the bottom's all 0, so it's just 2 equations with all those variables. Now what we're going to do is just get x equals and move the z and w over, move the z and w over, and that gives us this. So just to explain that a little bit, I add the z, I add the w, and that's how I get x equals z plus w. And then I add the z and minus the w, so y equals z minus w. So since I get x equals and y equals, and the w's and z's are over here, we can't determine those. Those can be anything. So we say w is something, call it t, any variable it could be. And then s is some other number. It doesn't depend on what y is. It can be anything it wants. So we call it s. If w is this thing t and z is this thing s, then y is this one, or no, this one minus the t minus whatever w is minus 1, and so forth. So let's see an example here. Basically what this is saying is we're totally free to choose whatever we want w to be. So w could be, I don't know, 5. Z could be anything. Z could be, I don't know, 3. If I do that, then y depends on, and that's why we call it a dependent system, y depends on whatever we choose for those. So this has to be 3 minus 5 minus 1. So z, or y, has to be -2, -3. And x has to equal whatever z and w are added together. So 3 plus 5. So that has to be 8. I could pick another example. W and z can be anything they want. It doesn't matter. I could have w be 5 again. Z could be 10. So then y has to be whatever z is, which is 10. Whatever w is 5. 10 minus 5 minus 1 is 4. And then x has to be the sum of the two. So it's 10 plus 5, which is 15. And then, of course, we can't graph these kind because there's no way for us to visualize 4 dimensions. So here is what I want you to do. I want you to answer these 3 problems. They're from your book. They're the self-check exercises on 2.3. At the end of the very end of the chapter, they have the solutions, so you can look here and pause it, or you can look in your book. This is what I want you to do absolutely after you watch the video. Now go to Moodle to see whether you have to do the extra assignment or whatever. So regardless of what's on your handout, I want you to do these problems after watching the video, and then go to Moodle to see what other work you may or may not have to do, depending on how far we got in class.